Alright, hello there guys. Uh, this video is actually going to be about factoring. We're going to have another video as well along with this one, discussing a different one of the teks. But for the most part, I just wanted to go over some factoring methods for quadratics, and then the factoring methods for cubic functions or cubic polynomials. They're the simple ones, and if you ever see them again, basically it'll just help you factor them a little bit faster. I do have a few tips for the cubic ones, so if you end up forgetting how to factor those out, or you forget the pattern or format, then you just use my tip and you should be okay. Okay. Now we're starting off with perfect square trinomials. Okay, there's two different types of perfect square trinomials. You have a format that looks like this: m squared x squared plus 2mnx plus n squared, or you can have m squared x squared minus 2mnx plus n squared. Okay, the only difference here is a plus and a minus, and whenever you factor them out, that's the same difference. You'll have a plus instead of a minus, or you'll have a minus instead of a plus, depending on what it looks like or what it is that you're factoring. Okay, now you see those m and n's. Well, you might be a little bit confused by these. Okay, well, is m squared and the n squared, these are just values that are squared. Okay, so m and n are numbers. Okay, I want to have this format like this because, well, for those that understand it, you'll see what it means right away. These are just numbers, meaning that these two are numbers as well, multiply times 2. But for those of you guys who don't understand, we'll have a number being squared. It means that it's just being multiplied by itself, and that's what replaces that m squared in the end. Okay, now m squared and n squared are going to be perfect squares. What are those? Well, these numbers are perfect squares. Okay, you might be able to recognize a few of them, but I don't assume that you guys remember all of these, at least not right off the top of your head. So what we're going to do is, well, I hope that you guys can practice these a little bit. I'll see if I can find some Quizlet, what's it called, those index cards, so that you guys can practice them on your own. You don't really need to know all of them. Hopefully you already know them up to 12. After that, maybe just remembering 15, 20, and 25 is a good idea, because these are common values that come up quite all the time, and just because they end in 5. Okay. Well, that's what would replace the m's and the n's, m squared and n squared, I mean. And m and n are just the numbers here. That's what would replace them. So m squared, you would want to treat it as, let's say if m was 1, well, m squared would be 1. If n was, like, let's say 6, then n squared would be 36. Okay, so that's all that's replacing those values. That's it. Let me create one. Let's say m was 6. Oops. Okay, m was 6 and n was 2. Okay, well then a perfect square trinomial made from these two values would be 36x squared plus 2 times 6 times 2x plus 2 squared, which is 4. Okay, now 2 times 6 times 2, that's 24. So we have 36x squared plus 24x plus 4 as a perfect square trinomial. Okay, well, I haven't shown you how to factor these yet. Well, if it's in this format, oops, I don't know why it keeps doing that. Sorry about that. Let me see if I can erase it. Hopefully it doesn't erase everything. It does. Okay. Well, these would be your factors. Okay, so if you have m squared x squared plus 2m and x plus n squared, your factors are mx plus n times mx plus n. Okay. So I said earlier that m was equal to 6, n was equal to 2. So the factors for this expression are just 6x plus 2 times 6x plus 2. Okay. So this is kind of nice because you just end up getting the same factor twice. Okay. And I said earlier, if we have a plus or we have a minus, all it is we change the plus or the minus. So let's say one of them was negative, or like let's say our expression, instead of being plus right there in the middle, we had a minus right here. Well, if we have a minus, well then this changes into a minus and this changes into a minus as well. So we'd have 36x squared minus 24x plus 4 is just equal to 6x minus 2 times 6x minus 2. Okay, that's all it is. Okay. The plus changes to a minus if there's a minus there. Okay. Alright, so let's go over another example. Let's say we had this value. Okay, you might not know what to do, or you might think, oh, I'm going to use the AC method. I'm going to take 16, I'm going to take 81, I'm going to multiply them together and see what I get. And then I'm going to try to get the factors of that. But 16 and 81 multiplied together is kind of a big number. You're going to end up getting a lot of factors from that. And it's going to be really hard, or it's going to take really long to check all of them. Okay. Well, in that case, just do this. Well, I recognize that 16 and 81 are actually squares. 16 is 4 squared. 81 is 9 squared. Okay. Well, the last thing I need to do to make sure that this is perfect square trinomial is, well, check to see whether 4 and 9 times 2 give me 72. Well, then I'll do that. 4 times 9 equals 36. Times 2. 2 times 6 is 12. 2 times 3 is 6, plus the 1 is 72. Okay, so that's actually the perfect number. Okay, because this is a plus, my factors are going to have a plus. Okay, so my factors are going to be 4x plus 9. And then my other factor is going to be the same thing. I've factored this out completely. I can't factor 4x plus 9 any further. I can't factor out this one any further because it's the same thing. So that's my final answer. You see? I didn't have to use the AC method. This was much easier. Just recognize your squares. Okay. Now the next one's also going to be a square. But this one's going to be the difference of two squares. And this one's a little bit different in the way that, well, if you notice, we don't have an x term right here in the middle. We only have two terms. And notice that this is subtracted. If it's not subtracted, well, you'll see that in the next slide. Okay, so still we're looking at perfect squares. M squared are the perfect squares, m itself are the numbers right here, n is the same thing. N squared is the perfect squares, n itself is the number right here. Okay, whenever you factor this out, it's almost like the one before, but instead you're going to have two almost identical factors, with the only difference being one of them is going to be adding the terms inside of it, and one's going to be subtracting the terms inside of it. So we get mx plus n times mx minus n. Okay, an example of something that looks like this would be something like, well, let's say 196. Okay, that's 14 squared. 196x squared minus, and then some other square, 64. Okay, so this is the difference of two squares. Alright, well, to factor this out, I just take m, which is the square root of this value right here, which is 14, x plus n, and that was 8, because 8 squared is 64. And then my other factor is going to be the same exact thing, but instead of plus, we'll have minus instead. Okay, that's it. Those are my factors for now. Okay, but that's easy when I relook at these. What about something like this? Okay. Well, I have two examples here. Well, I already know that 25 and 36 are perfect squares. I know that because I know that 5 times 5 is 25 and 6 times 6 is 36. Okay, so that's 5 squared, this is 6 squared. Okay. Once I see this, once I know that what the perfect squares are equal to, or what made those perfect squares, I can go ahead and write down my factors. We have 5x minus 6, 5x plus 6. And you see, this time I wrote down the minus first, I wrote down the plus second. Yeah, it doesn't matter. This is multiplication. They're both factors. So as long as one of them is minus, one of them is plus, you're good. The one for this one. Okay, well, I don't have a number in the front. Okay, that just means there's a 1. And 1 is just 1 squared. 4 is 2 squared. Okay, so the difference between, there's a difference, there's a minus. Okay, if there's not a minus, then you can't do this. So I can go ahead and write down my factors. We'll have 1x plus 2, and then 1x minus 2. That's it. Those are my factors. Okay, the only thing that you might want to write down differently is, well, we can have x minus 2 and x plus 2 instead. We don't have to write down that 1. It's up to you, though. So that's our factor form. That's our factor form for this one. And we can go ahead and move on. Okay, remember, you can always go back and look at it a little bit further. You can actually Google this stuff too. It's not too far from what I'm saying. And remember, this is difference of 2 squares. Okay, so so now let's look at something that's not factorable. The sum of 2 squares. The sum of 2 squares looks like this. It's basically the same thing as before, but instead of subtracting, we add. So an example of this would be x squared plus 4. Okay, this is going to be true for anything that's not a perfect square at the end. Okay, so this is not factorable, meaning that you cannot break it up into pieces. That's as far as it goes. Okay, now if you were to try to solve this for zeros for your solutions, like x squared plus 4 equals 0, you're going to get no real solutions. But you will get imaginary solutions. Or if you remember, those are also called complex solutions. Okay, and it doesn't have to be a square over here. X squared does have to be here, and you can have any number in front of it, like let's say 5. But this does not have to be a square. For example, x squared plus 3. Okay, x squared plus 3, not factorable. Okay, the sum of 2 squares, that's fine. The plus 3, it's still not factorable. Okay, now that also reminds me that let's go back one step. Okay, the same applies to this, the difference of 2 squares. Let's say you have x squared minus a value that's not a square. Okay, let's say minus 3. Okay, just like I did earlier. Well, if it's minus 3, we can still factor this out, but we start using radicals. That means we start using square roots. Okay, it's in the same format as before. Okay, whatever we have in the front, we'll leave. If we had a number in as a coefficient of x squared, we would have to take the square root of it. But actually, you know what? Just for the sake of it, let's say we had 2. 2x squared minus 3. You can actually still factor this out using square roots. They won't look nice, but every once in a while they come up. Okay, so if you have the difference of x squared minus something else, well, take the square root of the front value. And by the way, that's what we're doing over here. We're taking the square root of 25 and we're writing it down. Then we're taking the square root of 36, we're writing it down. Okay, now, and then you take the square root of 3 and you write it down. You write these down twice. And remember, because we're subtracting, one of them is going to be plus, one of them is going to be minus. Okay, and this is actually a factored form of this expression. although we tend not to want to use the square root symbols. If we didn't have the 2 on there, we wouldn't need that square root of 2. It would just be x plus square root of 3 and x minus square root of 3. You see? So if it's in this format, it can still be factorable. Yeah, that's it. Okay, I'm going to skip over this expression. Oh, okay, so these expressions, these are methods that also work on expressions that are in quadratic form. What do I mean by that? Well, let's take a look at these equations. Look at them. Right here we have x power of 4 instead of x power of 2. And then right here we have x power of 8 instead of x power of 2. Okay. Well, whenever you have these, we actually can still use the same methods that we just learned, or we just looked over. Like you see, we have 16x power. If that were a power of 2 minus 81, we'd be able to do that. Okay. So what if we changed it so that it looks like a quadratic, so that it looks like it has a 2? Well, if we changed x to the power of 4 into x power of 2 to the power of 2, then it kind of looks like a quadratic again. Let me try to write that down. Okay. It kind of looks like a quadratic again. Like if we just took the parentheses to be the variable, it's exactly the same thing. But then we take a look at our values. We have 16, we have 81, that's going to be 4 squared, we have 9 squared. Awesome. We can actually factor it out. It'll be 4, and then we take the inside of the parentheses, x squared. And then we'll have plus 9. And then we'll have another factor, 4x squared minus 9. Okay. Now this term right here, because we have a x squared and we have a plus, and we have no other terms, we don't have the x term, I can already tell that this is not factorable. But then we have this one. We have the difference of 2 squares. We have 4x squared minus 9. I recognize that 4 and I recognize that 9. Look at that. 2 squared, 3 squared. I know that I can factor this. Factorable. So I'm going to go ahead and factor this out. So we have 2x plus 3. And then we have 2x minus 3. Alright. Those are our factors. You see? And we started off with x to the power 4. We do not need to do... we don't need to learn complicated methods to factoring out x power 4, the polynomials of degree 4. As long as we know some methods with x power of 2, it translates. Okay? Well, depending on the format. The same thing can actually happen with things like this. Okay. Now, but for this one, we're gonna go ahead and do a little bit more factoring before we actually try to get the equation to quadratic form, meaning make it look like a quadratic equation. Okay. So for this one, well, let's take let's take our equation. And let's see if we have a common term that we can divide everything by. I couldn't do that here because 16 and 81 share no factors, but I can kind of notice one right here. 2, 10, and 12, they're all even numbers. That means that I can factor out a 2. Okay. After I divide by 2, or factor out the 2, we would be left with x power of 8. We would be left with 5x power 5, and then 6x squared. Okay, so I can factor out a number. Okay, we've learned this before. But if you notice, all these terms have an x as well. So I might be able to factor out a few x's along the way too. You always want to factor out the least number of x's for all terms, and that means that we're going to have to be able to factor x squared. So I'm going to go ahead and do that. By factoring out x squared, that means that you're going to take 2 x's away from each one of these terms. X power of 8 then becomes x power of 6. X power of 5 becomes x power of 3. And x power of 2 becomes, well, all the x's go away, so it just becomes 6. Okay, so now we have this. If you notice, right here, x power of 6 and x power of 3. Well, 6 is twice that of 3. Okay. I want to do this in quadratic form. So let's try to see if we can change x power of 3 as our variable. So, I'm going to put the parentheses around it. X power of 3 squared is the same thing as saying x power of 6. So those are our factors so far. Okay, now this kind of looks like a quadratic now. Let's say I changed it to this. Actually, let me use something that's not x, so that you don't get confused between the x's that the variables that I'll write here and these variables. Okay, so I'm going to change it. Let's call x cubed, that's going to be w. Okay, so we have w squared plus 5w plus 6. Now, let's factor this out. Well, we have a 1 in the front, and we have 6 over here, so all I have to do is take the 6 and factor it out. We have 1 and 6. We have 2 and 3. And those are all our factors. 1 and 6 equals to 7, and 2 plus 3 equals to 5. So it actually turns out that 2 and 3 are going to be part of our factors here. W plus 2, W plus 3. Let me write down that extra factor from the front, 2x squared. Okay, so 2x squared times W plus 2 plus W plus 3. Well, our final answer should use x's, so I'm just going to go ahead and replace that W back to x power of 3. Okay. Now, for now, since we don't know about the cubic ones, I'm going to leave them like this. But you know what? This actually seems like it could be completely factored out. Okay. So we have 2x squared times x cubed plus 2 times x cubed plus 3. I think that worked out pretty well. This would be our final solution until we learned about cubic functions. Okay. And this is factoring in quadratic form. Basically trying to turn equations into quadratic equations. Alright. And now, that was, hopefully you understood that was foreshadowing to the sum of two cubes. Alright, so sum of cubes, you want to learn some cubes. Okay. I would recommend knowing at least these 5 and knowing this one. Okay, maybe knowing 11, but there's actually a really fun way of learning the powers of 11 up to 11 to the power of 4, I believe, using a special triangle called Pascal's triangle. But I'll show that to you later if we have time. Okay. So sum of cubes just includes having a perfect cube in the front, having a perfect cube in the back, and then having x power of 3 next to the first term, or on the first term. Alright, so what you want to do here is, well, take whatever your perfect cube is, and we'll get rid of the cube, get rid of that power of 3. So that you only have m and n by themselves. Now this next part is kind of weird, but basically you're just taking the square of m, you're taking the square of n. Sorry, I think I rewrote these so that well, I think I originally used a and b for my expressions, but then I was like, hey, you guys, they probably looked at a, b, and c way too many times. Let's see some different letters. So yeah, sorry about that. This should be an n. Okay, so mx plus n times m squared x squared minus m times n. That means whatever this number is and whatever this number is, you multiply them together. You're going to subtract them away times x, and then you're going to add the square of the last value. Okay, so let's take a look at what this might look like. Well, m we can say is 2, n we can say is 4. Okay, so the original expression might look like this: 8 x power 3 plus 64. Now the factors of this would be 2x plus 4, and then we take our 2 and square it, which would be 4x squared minus, and then 2 times 4. 2 times 4 is 8, so that'd be minus 8 right there. And then we have plus our second value, which was 4 squared. So that's be plus 16. This would be our factored form of this. You see, it doesn't look like it, but like these two terms, they look a lot bigger than what this is equal to. But believe it or not, those are going to be your two factors. Okay. Now let's go ahead and give it a try with an equation, something we're not too familiar with. 64x power 3 plus 27. Well, 64 and 27, let's check to see whether they are cubes. We have x power of 3, so that's one of the conditions. 64 is 4 to the power of 3. 27 is 3 to the power of 3. So we can write that in. 64x cubed plus 27, 4x cubed, 3x cubed, 3 cubed. So let's go ahead and write down our factors. Our first factor, the linear one, will always have these two numbers in it. 4x plus 3. Okay, now we are going to be looking at the difference of two cubes as well. So if you can remember this part, the linear part, it makes it a little bit easier to remember the quadratic factor. Okay, so let me show you. We have 4x plus 3. The first value is always going to be the first number squared, so that's going to be 16, and then x squared. The second value, whenever we're adding two cubes, is going to be minus the product of the two numbers. 4 times 3 is 12, so that's going to be 12x. And then finally the last value is just the square of the second value, so 9. Okay, now notice how we have minus right here. Okay, once we look at the difference of two cubes, that's going to change. Okay, so this is the difference of two cubes. We still have a cube in the front, we have a cube in the back, we have a minus. For our factored form, the linear term is going to have mx minus n, basically the cube root of this value minus the cube root of this value. But take a look at this part. Yeah, these numbers are the same, these numbers are the same, even these numbers are the same, but the only change here is that a plus changes into a minus. Yeah. So let's look over an example. Let's say I'm going to go with an easy one. Let's say we have 1 cubed and x cubed minus 9 cubed. Okay, well this is just x power of 3 minus 729. Okay, since we recognize that we have a 1 cube and a 9 cubed in the front and in the back, those are going to be our n values and m values. So 1x minus 9. And then we have 1 squared, which is 1, x squared, plus 1 times 9, x plus 9 squared. So we have x minus 9, x squared. The 1 is there, but I just don't write it down. 1 times 9 is 10. I mean, not 10, 9. 9x, and then we have plus 81. Okay, so these are two of our factors for this difference of two cubes. Okay, notice that right here we have a plus now instead of a minus, but right here we have the minus. Whenever we were adding, we had the plus on the linear term and we had the minus on the quadratic term. They just change once you change the symbol in the middle. Okay. Next. Okay, so let's do an example. 8 and 125. I actually know these right off the top of my head. 8 is actually 2 to the power of 3. 125 is 5 to the power of 3. Our factors will be the first number, x, minus the second number. So 2x minus 5. Okay. And then inside of it, we'll just square the first value. 2 times 2, or 2 squared, x squared. Since we have a minus here, this one will be plus. Take the product of the two values, 2 times 5, x, and then finally add the second value squared, 5 squared. So we got 4x squared, 2 times 5 is 10, 10x, and then plus 25. So finally we get 2x minus 5 times 4x squared plus 10x plus 25. Those are our factors. Okay. Alright, so last problem, that's it. Factoring by grouping. Okay, so sometimes we're not going to be able to use any of those previous methods. Let's say we wanted to still try to factor this out. Factoring by grouping is exactly what it means. It's a lot like the AC method, where you split it up into, let's call it teams of values, and try to see if you can take out a common factor from each one of these groups. Okay, so the greatest common factor that you can. X power of 3 minus x squared minus 3x squared. Well, 1 and negative 3 don't really have any common factors besides 1, so we can't take out a value. But we can take out an x. You see, this one has x power of 3, this one has x squared. So I'm going to go ahead and factor out an x squared. Okay. It's a lot like the AC method, where we drew the line in the middle and then try to factor it out. Okay. Now, factoring out two x's, or x squared, will leave x cubed as x and negative 3x squared as minus 3. We do the same thing on the right hand side. Okay. Well, we have a negative 16 x plus 48. Well, 16 and 48 can both be factored by 4, but let's see if we can factor out a bigger value. 5 cannot fit in. 6 does not fit in both. 7 does not fit in either one. 8 fits in both, actually. 9 doesn't work. 10 doesn't work. 11 doesn't work. 12 doesn't work. It only works on 48. 13 doesn't work. 15 doesn't. 14 doesn't work, and 15 doesn't work. But 16 works. 16 divided by 16 is 1. 48 divided by 16 is 3. Because we have a negative in the front, I'm going to go ahead and factor out a negative 16. Okay, so I'm going to take that negative 16x divided by negative 16. That gives me x. I'm going to take the 48 divided by negative 16, and that gives me negative 3. Notice how we have the same factor here and here. Okay, now everything besides this, everything besides the stuff in parentheses, goes into its own set of parentheses now. X squared minus 16. Okay, I'm factoring out the x minus 3, so I'm only going to write it down once. X minus 3. Okay, so at this point, we've factored out quite a bit, and we shortened it. It's a much easier problem to do. Now, 16x squared, this is the difference of two squares. I know that 16 is 4 squared, so I'm going to change this into 4x plus 4 times x minus 4. And then I just bring down the x minus 3. And there goes my answer for here. Okay, now factoring by grouping isn't that bad, but it rarely comes up. Whenever we have x power of 3, it might be, and more terms, it might be something you might want to try out. It's exactly like the AC method that we've done before. but it won't always work out. Okay, I think I'll end the video at that. You guys have a great day, and I'll see you on the next video.